Press the bell icon on the YouTube app and never miss another update.
This is class 7 of 10th electric current. In the last class we have discussed about the factors on which resistance of a conductor depends and also resistivity of the material of the conductor. Smaller the resistivity of a conductor, greater will be the conductivity of the conductor, right? Metals have generally smaller value of resistivity and higher value of conductivity. Generally we use alloys, right? These alloys have resistivity higher than the resistivity of metals, right? Now we will take up another concept, that is resistor. A resistor is a device used to offer designated value of resistance in a circuit so that we can able to control current in a circuit, because we know that the current in a circuit I is equal to, it is V by R, where I is current, V is potential difference or voltage, and R is resistance, right? Generally, whenever we are using a cell or a battery, it has a designated value of voltage or potential difference, say 1.5 volt, 3 volt, 6 volt, 9 volt, etc. Right? Generally, we cannot vary potential difference of a battery. Right? Therefore, current in a circuit can be controlled by using a resistor, right? If we increase the resistance of the circuit, then the value of current decreases, or if we decrease the resistance, the value of current increases, right? So any device, right, generally it may be a metallic wire, right, pure metal or alloy, but generally in all electrical and electronic circuits, right, we use a device called as a resistor, right? It is a carbon composition resistor having a definite value. So a resistor is a device used to offer resistance in a circuit, right? Now we will take another concept, resistance of a system of resistors. Now these resistors are available in standard values, say 1 ohm, 2 ohm, 5 ohm, 10 ohm, etc. But whenever we need a particular value of current in a circuit, right, we need the appropriate or desired value of resistance. That desired value of resistance may not be available in the market, right? Suppose if we need exactly 1.25 ohm, right? Now this value of resistor is not available in the market. Maybe it is 1 ohm, 2 ohm, 3 ohm, 5 ohm, etc. Right? It is just like the currency notes. We are having standard currency note, 1 rupee, 2 rupee, 5, 10, 20, 50, 100, 200, 500, 2000. By the combination of this, we can produce any desired value of money. If you put 1 10 rupee and 1 5 rupees, it will become 15 rupees. Right? 1 10 rupee and 1 2 rupee, it becomes 12 rupees. We cannot print 12 rupee note. It is inconvenient. Right? Therefore, right, in electrical circuit, we use a number of resistors to get the desired value of resistance, right? Now these resistors can be combined or grouped in two ways, right? So two basic ways of combination of resistors. There are two basic ways of combination of resistors. Right. They are number one, series combination of resistor. Right. In series combination of resistors, right, the resistances are connected end to end, right, like this. Here we have a resistance R1, another resistance R2, third resistance R3. Right. These three are. When they are connected end to end, that is, one end of R1 is connected to one end of R2, and the other end of R2 is connected to this one end of R3, right, and so on. So such a combination is called a series combination of resistors, right. So next, second combination is, right, now parallel combination of resistors. Parallel combination of resistors. In parallel combination of resistors, the given number of resistors are connected between two common points, right? Say here we have a resistance R1. Here the resistance R2, and here the resistance R3. Right. Now, one end of R1, R2 and R3 are connected to one common point, say X, and the other ends are connected to the other common point, that is Y. Now the resistors are said to be connected in parallel. So if the resistors are placed right side by side, then that combination is series, right. Now if the resistors are placed one above the other, right, then that combination is a parallel combination. It is for our convenience, right. So a number of resistors are said to be connected in series if they are connected end to end. A number of resistors are said to be connected in parallel if they are connected between two common points, right. Now the thing is, what is the total resistance of this combination? That is called as effective resistance or equivalent resistance of the combination, right. Here these two are arranged in, these three are arranged in series, these three are arranged in parallel. In that case, we need to find the effective value of resistance, both in series combination and in parallel combination. Let us take it up one by one. Series combination and parallel combination. Now, we'll take resistors in series or series combination of resistors. A number of resistors are said to be connected in series if they are connected end to end. Now, let us consider three resistances of different values, R1, R2 and R3, connected in series. Like this. This is so three resistors of different values, R1, R2 and R3 are connected in series. Now let the combination, right, that means the two ends X and Y are connected to a battery a key and an ammeter. So an ammeter is a device. It is always connected in series with the circuit, that is end to end connection. This is a battery that provides a potential difference of V, right, between the two ends of the conductor. Right here, right, when the key is closed, a potential difference V is established between the two ends, right? That is the total potential difference across the combination, and a current I that flows through the circuit and through the combination. We know that the direction of conventional current is always from positive terminal of the cell to negative terminal of the cell. When we take this positive terminal, right, now the current starts flowing from positive terminal. Now it comes to the end X. When it flowing from end X to end Y, it has only one path, right? The same amount of charge flow per second through R1, R2 and R3. Therefore, current through each resistance is same, right? But potential difference across each resistance will be different, right? Here, this potential difference is V1, potential difference across R2 is V2, and potential difference across R3 is V3. Now, this can be measured by using a voltmeter. Now, these 3 voltmeters, right, gives the reading V1, V2 and V3. So, in series combination of resistors, right, resistors are connected end to end. That is first point. Second point is current through each resistor is same. It is because there is only one path for the flow of current between the 2 points X and Y. Now the third point is potential difference across each resistor is different. You have to remember these 3 points regarding the series combination of resistors. Now, let I be current V1, V2, V3, right, B and V3B, potential difference across, right, R1, R2 and R3. Right. Now we need to find what is the effective resistance of this combination or total resistance of this combination. Now from Ohm's law, right, we have V is equal to IR. Therefore, this V1 is equal to IR1, V2 is equal to IR2, and V3 is equal to IR3. Now, total potential difference across combination. Potential difference across combination, that V is equal to V1 plus V2 plus V3, or V is equal to, what is V1? IR1 plus IR2 plus IR3. Taking I common, I into R1 plus R2 plus R3. Let us take it as equation number 1. Right. So we see here when potential difference of V is applied to the combination, that produce a current I. Now this combination is replaced by a single resistor of equivalent resistance RS that produces the same effect as the combination. That produces the same effect as the combination, that is I, and this is V. So the three resistors, right, what the effect they produce is produced by the same single resistor. That means when a potential difference is applied across the single resistor, that produces the same current. Now from this figure we have V is equal to, right, I into RS. Let us take it as equation number 2. Right. Now, comparing equations 1 and 2, we have RS is equal to R1 plus R2 plus R3. This is the effective resistance of the combination of resistors in series. The effective or total resistance of a number of resistors connected in series, right, is equal to the sum of the individual resistances, right. Now, in series combination of resistors, the total resistance of the combination increases, right. So this is how we can obtain the equivalent resistance or effective resistance of the combination. Now we shall take up resistors in parallel. Parallel combination of resistors. Again here we need to find the effective value of resistance. Now let us consider three resistors. R1, R2, R3. They are connected to a common point. X and Y. Now a battery is connected to the circuit along with the key. Now a potential difference V is applied across the combination. Now potential difference across R1 is equal to potential difference across R2 is equal to potential difference across R3. In series combination, one end of R1 is connected to positive terminal of the battery and the other end of R3 is connected to negative terminal of the battery. Right? R2 and the other ends of R1 and R2 are not connected to the battery. But see here R1, R2, R3 are directly connected to the battery. So here between XY is applied across R1, R2 and R3. So in series parallel combination, potential difference across each resistance is same. Now let I be the current drawn from the battery. Now when a current comes to this end, it gets divided because between X and Y, the current will find three paths, right? So the charges get distributed along three paths. Say here I1, a current flows through it, I2 through R2 and I3 through R2, right? Here if we connect a voltmeter, that voltmeter measures potential difference across each one. Here we will use an ammeter that measures, right, current I1. The second ammeter connected between X and Y to R2 that measures I2, and the third ammeter, it measures the current I3. Now this is the circuit diagram, right? Now the first point is that in parallel combination, resistors are connected between two common points. So here X and Y. So X and Y are common to R1, R2 and R3. Now here potential difference across each resistor is same. In series combination, potential difference across each resistor is different, remember. Now the third one, current through each resistor is different. You have to remember this point. Series end to end, parallel between common point. In series, current is same, potential difference is different. In parallel, right, potential difference is same, current are different. Now, let I be B. Potential difference across each resistance. I1, I2 and I3. B. Currents through R1, R2 and R3. Respectively. Now, so from Ohm's law, V is equal to IR or I is equal to V by R. Therefore, this current I1 is equal to potential difference by R. Right. Therefore, I1 is equal to V by R1. Now what is this I2? I2 is equal to V by R. I2 is equal to V by R. And I3 is equal to obviously V by R. Now we have main current. So I is equal to I1 plus I2 plus I3. The same current flows here, that is I. Here to measure I, we can connect another ammeter that measures a current I. Or I is equal to I1 V by R1 plus I2 V by R2 plus I3 V by R2. Or I is equal to, taking V comma 1 by R1 plus 1 by R1 plus 1 by R2. Let us take it as equation 1. So, the effect of this combination of resistors in parallel is to give a current I when a potential difference is applied. Now that combination is, say, replaced by a single resistor of effective resistance Rp when connected to the same battery. It produces the same current I. Now, so for single resistor, here Rp is that single resistor or resistance of that single resistor that produces the same effect as the combination. So current through the single resistor I is equal to V potential difference by resistance Rp. Equation 2. Now comparing equations 1 and 2, we will get 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Now this is the total resistance or effective resistance of three resistors R1, R2 and R3 connected in parallel. Now left hand side of the equation is the reciprocal of effective resistance. It is not Rp, it is 1 by Rp. Right hand side 1 by R1 reciprocal of R1, 1 by R2 reciprocal of R2, 1 by R3 reciprocal of R3 and their sum. Therefore, the reciprocal of effective resistance of a number of resistors connected in parallel is equal to the sum of the reciprocals of individual resistances of the combination. So this is parallel combination of resistors, right? Now, let us take some point to understand combination. Now let two resistors R1 is equal to 3 ohm and R2 is equal to 6 ohm. Suppose in series, if they are connected in series, then the effective resistance Rs is equal to R1 plus R2, because in series Rs is equal to R1 plus R2 plus R3 for 3 resistors. For 2 resistors it is R1 plus R2. For n resistors R1 plus R2 plus R3 plus R4 plus etc. Now this is equal to 3 plus 6. That is equal to 9 ohm. So what is the effective value? It is greater than the greatest resistance of the combination. That means in series combination of resistors, the total resistance or effective resistance is always greater than the greatest value of resistance of the combination, right? So in series combination, so effective resistance increases. So whenever we are having smaller values of resistors and we need a higher value of resistance in a circuit, they can be used in series combination. Suppose if the two resistors are connected in parallel, if they are connected in parallel, then 1 by R1, 1 by Rp is equal to 1 by R1 plus 1 by R2. That is equal to 1 by 3 plus 1 by 6. Or 1 by Rp is equal to, taking 6 LCM, this is 2 plus 1. That is 3 by 6. That is 1 by 2. Right? Therefore, Rp is equal to 2. Now we see it here. In parallel combination, the effective value is 2. What is the least value of resistance of combination? 3 ohm. So, in parallel combination of resistances, the effective value is always less than the least resistance of the combination, right? Therefore, in parallel combination, the effective resistance decreases, right? So, in series combination, the effective resistance increases, whereas in parallel combination, the effective resistance decreases. So these points has to be remembered, right? You just while studying both series and parallel, you study series combination, you study parallel combination, then you compare these two regarding how they are connected, what about current, what about potential difference, what about the effective resistance. Series, end to end, current is same, potential difference is different, effective resistance increases. Parallel, right, connected between two common points, potential difference is same, current is different, effective value of resistors decreases, right? That's all about series and parallel, right, combination of resistors.